Have you ever really stopped to think about the magic of sending a photo to a friend? I mean, you tap a button, and in an instant, it flies across cities, maybe even oceans, and just appears perfectly intact. We do it all day long, but behind that simple act is this absolutely revolutionary science. So let's pull back the curtain on the theory that makes our entire digital world possible. I mean, just think about the scale of this for a second. Every single moment, there's this unbelievable flood of data, videos, messages, you name it, zipping around the globe. How does it all get there? Not just fast, but with almost perfect accuracy. It seems like it should be an impossible mess. But the answer, it turns out, starts with a really simple idea.
And this is it. This is the blueprint. Every single act of communication, whether it's a smoke signal or a 5G data stream, follows this exact path. You've got a source, a transmitter, a channel, which is usually full of noise, a receiver, and then finally a destination. This whole map was laid out by the brilliant mathematician Claude Shannon, and his information theory gives us the rules to master this entire process by focusing on two really critical goals: making communication efficient and making it reliable.
All right, so first things first. Before we can even talk about sending information efficiently or reliably, we've got to nail down a really basic question. What is information anyway? And the answer might actually surprise you.
Think about it this way, right? Dog bites man. It's boring. It's expected. You don't really learn much. But man bites dog. Whoa, now that's news. It's totally unexpected, it's surprising, and in the world of information theory, that element of surprise, well, it's everything.
So here's the key insight. Information isn't really about meaning. It's all about probability. Finding out the result of a coin flip, that gives you a little bit of information. But finding out the winning lottery numbers, well, that resolves a massive amount of uncertainty. And because of that, it contains way, way more information. Surprise is the currency here.
And we measure all this uncertainty, all this information, in a unit you've definitely heard of, the bit. A single bit is just the answer to one simple yes or no question, like that coin flip, and it cuts our uncertainty in half.
Okay, so now that we've got a handle on what information is, we can tackle that first big challenge Shannon laid out: efficiency. How do we say what we need to say using the absolute fewest bits possible? This is the whole science of data compression.
Shannon gave us a way to measure this, and he called it entropy. You can think of it as the average amount of surprise you can expect from any given source of information. This number he called H. Well, it tells us the absolute, rock-solid, unbreakable limit. It's the pure, essential information with all the fluff stripped away. You literally cannot compress a file any smaller than its entropy without losing some of it.
So how do we get as close to that limit as we can? Well, the strategy is actually super intuitive. Think about the English language. The letter E is everywhere, right? But the letter Z is pretty rare. So it just makes sense to use a really short code for E and a much longer one for Z. By doing that for every single letter and symbol, we can dramatically shrink the total size of our message.
And this brings us to the other side of the coin. Shannon had this really simple but powerful way of defining everything that gets left over. If entropy is that pure, core message, then redundancy is just everything except the information. It's all the predictable stuff, the wasted bits, the fluff we can get rid of to be more efficient.
All right, so we've compressed our message. We've squeezed it down to its purest, most essential form. But now we slam into our second huge challenge: reliability. How on earth do we send that perfectly concise message through the real world, a world that's always noisy and imperfect?
The thing is, every communication channel, I don't care if it's a copper wire or the air itself, it has noise, static, interference, random glitches that can flip a 1 to a 0 or a 0 to a 1. For decades, the thinking was you had a choice. You could send data faster or you could send it more reliably. You couldn't have both. And then Shannon came along and proved that was completely wrong.
He did it by defining this thing called channel capacity, which we call C. Just think of it like a fundamental speed limit for any channel, like the speed limit on a highway. This number, C, is the absolute maximum rate you can shovel data through that channel and still be able to fix any errors the noise causes.
And this right here is the heart of his second amazing theorem. It basically says that as long as your data rate, which is R, stays below the channel's capacity, C, as long as you're under the speed limit, you can achieve error-free communication. Not almost error-free, as close to perfect as you could ever want. But if you go even a tiny bit over that speed limit, the whole thing falls apart and errors go through the roof.
And look, this isn't just some abstract idea. We can actually calculate this limit for a real channel. So for example, on a specific noisy channel, the absolute top speed for reliable communication might be something like 0.397 bits per symbol. That's not a guideline, it's a fundamental property of that channel, kind of like its own personal speed of light.
So, how do we pull off this magic trick? The solution is something called channel coding. And here's the beautiful, almost ironic part. We do it by intelligently adding redundancy back into the message. Yeah, the very same stuff we worked so hard to strip out for compression, we use those extra bits to build these clever error-correcting codes. These codes create patterns that let the receiver spot and fix any errors that happen along the journey.
So let's bring these two giant ideas together, right? Shannon basically gave us the complete instruction manual for all digital communication. And the truly revolutionary part was that he showed we could solve these two big problems, efficiency and reliability, separately. First, you compress the heck out of the message down to its core, and then you add just the right amount of clever redundancy back in to make it totally immune to noise.
And it all comes together in this one beautiful equation, the Shannon-Hartley theorem. This is, no joke, one of the most important equations of the entire 20th century. It connects that ultimate speed limit, the channel capacity, to two real-world things engineers can actually measure and work with, the channel's bandwidth and its signal-to-noise ratio. It is the foundational formula for our entire digital world.
So, to just wrap it all up in a neat little bow, for the problem of efficiency, the big question was, how do we be concise? Shannon gave us the limit, entropy, and the tool, source coding. Then, for the problem of reliability, the question was, how do we be clear? He gave us the limit, channel capacity, and the tool, channel coding. Two problems, two fundamental limits, and two brilliant solutions. That, right there, is the elegant heart of information theory.
What Shannon did was give us the mathematical certainty that perfect communication was even possible, and then he drew us the map to get there. It completely changed the world, which it kind of leaves us with one final big thought. His theory was all about the flawless transmission of information. What's the next great revolution going to be? Maybe a theory that can finally tackle not just the transmission, but the meaning itself.